time constant tau, or RC time. The time constant affects on the capacitors voltage charge up slash discharge is dictated by the complete response. In other words, we know that the complete response is then going to be V initial e to the minus t over tau plus V final one minus e to the minus t over tau. So if I write this in detail, we're really talking about Vc of 0 minus times e to the minus t over tau plus VOC times 1 minus e to the minus t over tau. What we're finding here is that this is what actually happens here. So the final voltage, let me be careful, the initial and final voltages are proportional to two functions. In other words, we can clearly see that VC going towards VOC, and let me be careful here. So we're finding that we have VC of 0 is e to the minus t over tau versus VOC times 1 minus e to the minus t over tau. And so what we're looking at is that this guy is a percentage. Just like this quantity is also a percentage. And what we're finding here is that these values show information at the rate of decaying or increasing of the natural and forced response. So if I plug in my table here, this is what I have. We don't care about the time per se. We only care about the time t over tau, since that's what's in the exponential term. So I'm looking at 5 time constants, and you could see that the exponential And the second column, that's a percentage. So I multiplied it by 100%. And then I have 1 minus E, and that's also a percentage. But what you're seeing here is that there's a very quick decay, and there's a very quick charging up the capacitor. So what I'd like to do is that draw pictures and clearly show what we're having. So I'm looking at the decay of the natural response. So if I look at the decay, so I'm going to move these things around just to get them symmetrically on the page. Here's what I'm seeing. And the way I'm going to do it is I'm going to use bar diagrams. So if I look at this, one of the things that you want to pay attention to is that when it decays, it's actually talking about the current of the capacitor, which is proportional to the voltage of the capacitor. So if I draw this out, a capacitor that's fully charged then must have a voltage that's, let's say it's 4 squares. I don't know how to scale this. You'll have to bear with me. 4 squares look something like this. So this is a capacitor voltage when it's fully charged. So this value right here is VC of 0 minus. Now, if I call this 0 and I call this, let's say, 50%, then each of the lines tells us what's going to happen. Now let's look at the first one. After one time constant, it drops down to 37. So it's got to be below 50. So if I look at this, I'm going to say that this guy is our discharge at tau. And then the second one goes to around 14%. So when I look at 14%, if this mark here is 25, it's got to be smaller than that. So I'm going to say that this guy might be around right here. And this is going to be at 2 tau. So when I get to 3 tau, you could see that it's 5%. So now we're talking about splitting hairs here. What's 5% of this guy? I don't know. Maybe something like this. And then it's got to get even smaller. And then it's got to get even smaller. So these things are really tiny at 3 tau, 4 tau, 5 tau. So if I'm looking at how you're discharging from the initial voltage, well, you can kind of guess here that this curve has to look something like this. And at 5 tau, you could see that it's effectively 0. So if I come in and I put my numbers, this should be 37%. This should be, well, I didn't do my curve very well, as you could see. This would be 14%. This would be 5%. This would be 2%. And now I'm going to say that I'll round up, and this is at 1%. So it decays really quickly, which we've already shown that to be the case. Now, if I look at the, I don't know, the charging up of the forced response, we have to play the same game. I now have a discharged capacitor. So if I have a discharged capacitor, what I'm imagining here is that it has to start off at 0 here. So at this point, I'm going to say that this is 0. So at 0 tau, there is none. But now let's look at the table. It jumps up to 63%. So this mark here, right? If I look at this mark is 50%. This mark is 75%. And then this mark, of course, is 100%. So if I look at 1 tau, it's up at 63%. So let's draw that at 1 tau. So at 1 tau, it's got to be somewhere around right here. So you could see a fairly big jump at tau, just like the table says. And then you'll see that the next jump goes up to 87%. Where's 87%? I'm going to say it's roughly right here in the middle of this guy. And then if I keep going, then it jumps to 95%. So we're up here very, very, very quickly. So we're going to say that maybe that might be 95. And now I have to get to 98 and 99. So these are just minuscule changes here. In fact, it's a very painful increase at the very end. It looks like it's fully charged, but it's not. It doesn't get there. So if I'm looking at this, we'll do at 2 tau, 3 tau, 4 tau, 5 tau. And if I come in and look at these squares here, you're seeing the growth is quick initially, but it sure does slow down later on. So now if I look at how this thing grows, what am I seeing here? I'm seeing a curve that looks like that, which is the RC curve. So if I start putting in my numbers to 2 sig figs, I would say that this is 63%, 87%, and then we have the crawl, 95%, 98%, and then we get to 99%. And to get to, fully charged value, it takes an infinite amount of time. So what is the time constant showing us? The time constant clearly defines how quickly the capacitor charges up to the final while the capacitive current which is proportional to the resistor voltage decays to 0 from VC of 0 minus. So even though I did not put this, I would say that VOC here is the 100% mark. Now, the charging curve is exponential, right? since the charging curve is exponential, in theory, the capacitor takes an infinite amount of time to fully charge up. Yeah, it takes an infinite amount of time to charge up, but look how close it is to fully charging. Therefore, it never reaches 100% of VOC. For practical purposes, after 5 time constants, in other words, 5 tau, one claims the capacitor to be charged. It's not fully charged, but it's close enough.